Thanks so much for being here. Joey and I were going to give this talk last year, so this has been long delayed, and we're both really excited to be here. I'm Mike Dodds. This is Joey Dodds, no relation. We're going to talk about verified cryptography. So the idea here, the domain we're working in is formal verification of code. So, I mean, everyone here has probably done kind of sort of first year mathematics at school. You remember Pythagoras' theorem? So Pythagoras' theorem tells you a relationship between the length of the edges for a right-angle triangle, and it works for any right-angle triangle. Well, you can sort of think of formal verification as analogous to that. So what we want is to prove a relationship or a property of a piece of software for any input or situation. So this is a little bit stronger than what you might think of as testing, where we just do it for one input or situation. And just like with Pythagoras' theorem, we're going to use the machinery of mathematical proof. We're going to use formality. We're going to use kind of reasoning in order to do that. So this talk in particular, we're interested in cryptographic primitives. And these are really the building blocks of security. They're things like AES, SHA-2, ECDSA. And one of the things that's distinctive about this is that you all are probably using this software right now, just sitting there in your seats. You know, every time that your device talks to a remote device, it's calling into some of these primitives. And so that means that this is very kind of important software. And as well as kind of like more conventional things like AES and SHA-2, like hash functions and block ciphers, you also have things that are kind of more exotic, like we recently saw post-quantum libraries that are resistant to quantum attacks, and blockchain-specific libraries. So there's a big world of these kind of primitives, and these primitives are things we want to get right. These have the kind of quality of being at the root of a lot of security. They're way, way down the stack. And so, you know, sometimes if there are mistakes, you can have this kind of picture here, this very famous XKCD strip, where it turns out that everyone was relying on some sort of piece of software that was built by someone in 1992 and has been maintained ever since. So it's always important when you do a proof or any kind of assurance methodology, I think, to start by asking, like, who cares? Whose life is going to be improved if we do this work? In the case of cryptographic libraries, I mean, the good news is that this is kind of some of the most used software on Earth. You know, there are billions of users, there are millions of calls per day. Every cloud service, every device, every washing machine probably calls into these kind of primitives. And this means that they're security critical across every possible dimension, really. Now, that would be fine as long as the code was relatively easy to understand, but in fact, the code is incredibly gnarly. And the reason is because it's highly used software. When you're digging into that, when you're sticking something in a critical path on every message, every packet, then it's really important for this thing to run quickly. And that means that the software itself is incredibly hard to audit. But the good news is that there are a small number of libraries that cover nearly all the use cases. And the code's also highly encapsulated. So this means that it changes very slowly. So this means that we have some chance to improve the situation. We can get to a point of confidence with this code. So this means that we formally verify this code. We can formally verify code for everybody. And that means that, you know, we can kind of move on to more exciting problems. This is already exciting enough for me, but maybe you don't agree. So just a bit of kind of self-promotion. You might want to ask who did the proofs anyway. And it was, I'm part of an organization called Galois. We're a 90-person industrial lab based in Portland in Oregon. And Galois is, you can sort of think of it as a computer science research department that sort of, I don't know, sailed off to make its fortune in the world of kind of industrial research. So our favorite tools are automated solvers, interactive theorem proving in sort of safe programming languages, fancy type systems, and we've been deeply involved with the Haskell community for many, many years. And while it feels kind of grubby to say this, we are hiring. So come and talk to me. So I think that part of the message here, part of the sort of story here is that we do difficult proofs. These proofs are incredibly hard. They're incredibly dense. We've verified some really critical pieces of software. So here's a couple of papers here which you can read about verification of S2N, which is the TLS stack, which is used in Amazon. We also did a paper recently about verifying some core components of AWS libcrypto, which is an OpenSSL fork. And we've also been working on this thing called the BLAST library, which is a signature library mostly for use in blockchain applications. All three of these are production grade industrial pieces of cryptography They weren't substantively modified when we verified them. And that means that we have those proofs out there, they're working, and they're kind of protecting these pieces of code. And we know that that means that that's going to save them from some kinds of errors. So I think it's worth backing up. The world of formal verification is very large. And so it's worth asking, like, what do we mean by verification? Why is verification for us? One of the nice things the last few years has been that verification technologies have made their way out into lots of different places in the world. But that means that there's actually like not one thing that's verification. So what do we mean by verification for us? The first thing to say here is that really, when you think about a threat model for cryptographic systems, so when we say verification, you really need to say verification of what, by what? And so the reason why, why do we verify these particular properties? In the case of cryptography, we're mostly interested in code crashes and code that doesn't implement the algorithm correctly. And so the reason that we worry about code crashing is because these cryptographic primitives are running deep inside the system. So they're being run in the sort of places where if they were to crash, if they were to generate undefined behavior in LLVM sense, they'd be able to write outside of memory bounds. And in that case, you would be able to break the security model of the system. You can imagine sort of like a kind of bad packet coming in and then sort of generating a vulnerability, being able to write over internal memory. The other thing that might happen, which in sort of some ways is, I think, less of a concern because it's only on a single packet basis, it's not owning the actual machine, is that you might not implement the algorithm correctly. So you might not compute AES GCM for some inputs. Now, in that case, well, you might just have a situation where there's a flaw in your implementation. It might be that you don't your messages aren't protected. And that means you could decrypt the message in transit if someone found out about it. So we want to stop both of those things. Now, there are a couple of things which are excellent targets of formal verification, but we don't actually address. One of them is side channels, things like microarchitectural channels, energy and timing channels. Those things are really important, but the tools we have don't address those. You need different tools to do that. And the other thing that we don't talk about is cryptographic security. So many of you will probably have seen the Psych cipher, which was broken recently for kind of more sort of like algorithmic reasons. Well, we don't address those. We assume that the algorithm is correct, and we just say, do you address the kind of errors here? And that's because I think in general, you're more likely to get errors at that level. I mean, the errors you get in the algorithm are really bad, but you hope that they don't happen too often. And again, you need different kinds of tools in order to kind of prove those things correct. So verification for us is, people will talk about Hoare logics and higher orders and types and things like this. For us, formal verification just means a complex thing is the same as a simple thing. So a complex program is the same as a simple program. And a simple program is a reference implementation or a specification, or you can think of it that way. So that means that for us, formal verification is just really fancy testing. So when you talk about testing, you say that the program applied to some input doesn't crash, and the program applied to some input is equivalent to some expected result. Well, now we can just use logic to say, like, maybe just let's add a quantifier here. So formal verification says, for all inputs, the program doesn't crash, and the program input is the same as the specification input. So seen this way, what we're trying to do with formal verification is just to achieve, like, dramatically higher coverage over the input space. So if we think about this from hash-based message authentication code, HMAC, then let's just think about what that looks like. So we've got the boring SSL HMAC code, and we've got the book HMAC, which is RFC 2104. So on the left-hand side, we've got some code, which please do not read. It's actually from the AWS-LC, which is the library that we were working with. But it's the same as the boring SSL one, more or less. And so this is just like a big blob of C code. It's got like a bunch of functions, it does a bunch of things. It's actually rather hard to understand what it's doing at any given point. And HMAC is one of the smaller primitives. And then we want to say that it's equivalent to what the book tells us. And the book says that the HMAC is just this, basically it's just this one line of text. We've got this hash, and then we've got the XOR of this OPAD and IPAD structure. So one of the nice things about HMAC in particular is that it's really very simple to write down what it looks like in terms of, like, it's really very simple to look it up. So other AES is a little bit more complicated. Okay, so we can't really take that RFC definition and just feed it into a theorem prover. There's no way of it's not written down in a way that allows us to do that. So what we want to do is to get as close as possible to that RFC definition, but in some form that the computer can understand. So, Galois is all about domain-specific languages. So what we did was, many, many years ago, we built a domain-specific language called Cryptol, which is intended for writing down block ciphers and cryptographic specifications. So what we've got here is on the top here, we've got the RFC definition. And then on the bottom, we've got the Cryptol definition, which is, if you're at all into Haskell, it's not too far from a Haskell definition. And you can sort of see through the coloring that the structure of the HMAC definition on the bottom is kind of rather structurally similar to the structure of the HMAC definition on the top. So we have the two arguments, the O key and the internal piece, and the internal piece is this kind of hash of this K piece. So the idea here is that the cryptographer can take a look at this, and hopefully they can trust that this is actually close enough to what they're looking for, that they don't feel concerned that there's any major discrepancies here. And so we've done this for AES, GCM, and SHA, and ECDSA. And then when we do proofs, what we're doing proofs against is these specifications. So then we have the theorem. This is the theorem of a sort that we want to prove. So on the left-hand side, we have the boring SSL HMAC code. And on the right, we have the Cryptol HMAC specification. And what we want to do is to say that for all inputs, that we get the same output for these two programs. And then you can imagine that when we're talking about ASGCM or something like that, the code is much more complicated, but the specification stays simple. And so we want to kind of prove this theorem. The way that we do this is we have a proof tool. So this is a tool for proving properties about programs. And so this is kind of a little architecture here. I won't go into too much detail about exactly what's going, but it gives you a sense of what's going on here. So on the left-hand side, the inputs here, we have the program, which is in LLVM or Rust or Java or C. And then we have a pipeline, which will get to the point where we can say that it's verified or not. And we also have as an input the Cryptol specification. So what we're going to do, and this is really the secret sauce of our proof tool, is symbolic execution. So concrete execution, you take a single input and run the program. For symbolic execution, you run the program, but you leave some of the inputs as undefined. So, if you say that y is less than 7, well, that will turn into a logical formula that tells you the meaning that the program sort of claimed that y was less than 7. And so what we have in our proof architecture is a very precise symbolic execution tool that lets you take real-world pieces of code and then convert it into symbolic models. So these symbolic models represent all the properties of the program in sort of a mathematical form. So the other thing that symbolic execution does is it proves that the program can't crash. So it proves that you can't get those undefined behaviors. And so just in the same way as normal execution gives you, tells you that it doesn't crash because you got to the end of the program, you didn't see the crash. Symbolic execution proves that the program can't crash for any of the inputs that we're talking about. And the output that we get is a term, which is a mathematical model of what the program is doing. So it sort of represents, it allows you to say the input variables and the output variables, it relates them as a relation. So then we do the same thing for the Cryptol specification. It's much easier for Cryptol because with Cryptol, it's specifically designed as a language for specification and verification. And then we take these two terms and then we pair them to each other. Usually we use an off-the-shelf mathematical reasoning tool called an SMT solver. And so when we kind of compare these two terms, ideally, the kind of ideal term, Joey will explain why this doesn't actually hold, but the ideal situation is that we just kind of run the program symbolically, we run the specification symbolically, we give it to the SMT solver, we give it to, it tells us that it's verified, and then we'll go home. Or it tells us that there's a bug. Of course, the other thing that can happen is it can time out. So this is, never very edifying if it happens, but it's part of the problem of doing proofs. So the results of these proofs are a really high confidence of this property. So for all of the inputs, the primitive that we were looking at doesn't crash, and the primitive produces the same output as the Cryptol specification. So we've proved this for a whole load of primitives. So AWS Lib Crypto, we did HMAC, SHA, a whole bunch of other things like elliptic curve. We've verified a lot of things for the S2N TLS library, including the TLS 1.2 state machine, DRBG, and HMAC. And for BLST, we verified all operations, although in the case of BLST, the only things we verified were the absence of crashes. You still need to do some reasoning about behavior in that case, but in the absence of crashes is the main thing that they were concerned about in the case of BLST. So we have these kind of properties here. So this picture I think I painted sounds very, very simple, but actually the kind of mechanics of the proof are rather complicated. So I'm going to hand over to Joey to talk about how we actually accomplish these things. Thanks, Joey.
Yeah, so that was the nice rosy view of what things look like from the top, and now I get to bring all the illusions of how nice and simple it was crashing down. So if you're familiar with formal verification, you've probably seen a number of efforts targeting cryptography. The purpose of this slide is just to kind of explain why it's such a juicy target for verification people. One of the properties is this code is mostly bounded in input size. So the AES block function, for example, takes a fixed amount of input in, it puts a fixed amount of input out. That's really friendly for verification, which has a lot of trouble as things tend to get unbounded. In our technique, we can just unroll loops directly, which means we turn loops into not loops, and we just have to reason about them as straight line code. Static data structures make life easier again, especially in a language like C, where memory is really hard to deal with. Dealing with linked lists, dealing with whatever sort of map implementations people invent in C is a lot of work. So when we're in the world of cryptography, we're mostly dealing with straight arrays of data, which are quite a bit easier to reason about. If you think about what Mike just showed us about HMAC, there's a really clean description of what an HMAC should look like. If you think about a piece of software you work on from day to day, you might not be able to come up with such a nice one-line specification of what it should do. In cryptography, there's usually a very specific design, and everybody in the world is trying to implement that design. So that gives us a really clear target for verification. And code is extremely stable over time. This AES GCM code, for example, I think was mostly written in the early 90s, and it's barely changed since, which in many ways is a credit to the people that wrote it in the first place. It's incredibly high-quality code, and it's been optimized to within an inch of its life. There's not much more to do with it. So what this means is, when Mike said this code is running on everybody's machines, he's talking about a very specific piece of code that has been sort of cloned across a number of projects and efforts, but the sort of origins of the vast majority of these implementations is actually sort of this original implementation that sort of survived over the years. So unfortunately, software that's difficult to write will generally be difficult to verify. There is an exception to this rule, I'd say, which is that some software is difficult to write because you really have to work to sort of nail the abstraction and get just the right interface and just the right representation. That sort of work tends to actually make verification easier. What this slide's talking about is when things get hairy, when things get complicated, when you have to dig deep into, like break the abstractions of the hardware to get the most optimization you've hoped for. That sort of thing tends to increase the difficulty of verification. And when you think about it, it's kind of obvious why this would be the case, right? We're trying to sort of draw this connection between this book HMAC, whatever was in the RFC, and the HMAC as it appears in OpenSSL. And intuitively, sort of the more we increase the distance between these things, the more work it's going to be to sort of write the proof. So one of the things that we tend to do when we write these proofs is we tend to layer the proofs. So we'll take our book HMAC and say, maybe apply one optimization to it, and we'll prove that that optimization holds. And that sort of bangs HMAC a little more into the shape that we'd want to see it to get it to the point that OpenSSL HMAC's at. And then we repeat the process, maybe picking another optimization, maybe picking a different shape of the code. And we do this a number of times until we get all the way to the implementation that we want to prove. And these are a number of the things that can come into play here. The good news is actually sometimes if you take, like, for example, if you take multiple platforms, some of the optimizations will be common across all of the platforms. So you can sort of almost have a tree of proofs in a sense, where these branch off as things get differently. So this is actually an advantage in terms of being able to reuse the proofs. But there can be a lot of different implementations, and actually, as we sort of moved from the world of C to the world of assembly, we were kind of shocked at how many different implementations you might find of the exact same thing to make it run well in all sorts of different situations. And in general, each step in this process is going to require some theorem about the code. So it'll be saying this optimization is actually correct, or saying this way of refactoring the code is valid and preserves the behavior. So as nice of a target as cryptography presents for verification, it's a really difficult target as well, in particular because of the degree of optimization. You sort of get more bang for your buck out of each optimization in cryptography than you will almost anywhere else. You know, to the extent that x86 implementations have multiple instructions with the sole purpose of making AES run faster. One is an AES instruction. There's also instructions for the authentication side of AES GCM. And that has made AES the implementation of choice on these particular processors. A lot of the optimizations, especially as we look into programs like BLST, which BLST is based on pairing friendly curves, which is sort of, it's all based on field arithmetic, group arithmetic. People spend a lot of time taking these reasonably straightforward mathematical operations and, for example, figuring out how to defer a modulus as long into the execution of the program as possible. Because in general, the fewer modulus operations you can run, the faster your code's going to run. But it just takes us farther and farther away from sort of the standard book implementation as we get into our actual implementation. And a lot of optimizations tend to break abstraction boundaries. I think we're going to get to an example of that in a minute. So Mike mentioned that the tools are going to kind of tell us yes or no. Unfortunately, far more often they spin forever and they never come back to us. And so one of the main things you do when you're doing this kind of verification is try to figure out how to control the complexity in order to get some feedback from the tool. These are the tools that you can use when you're using a tool like SAW. In this case, change the code is a wonderful option, but it was not one of our options in any of these efforts because the customers for these proofs wanted things to run the way they'd always been running. It's super old code, it's super stable code. Changing it would have, the only reason that would be acceptable to change it is if it was just wrong, which fortunately was not the case. But changing the code can be very powerful. One of the reasons is this idea of getting the right abstraction, this idea of writing things down correctly and in a way that the tool is going to understand. You find a remarkable correlation between what people are able to understand about code and what machines are able to understand about code. So the other thing is sometimes you just have to get to know the solver and you have to sort of change things in such a way that the solver is going to be happier with it. Honestly, that's one of the really frustrating parts of doing this kind of work is that the solver can be remarkably unpredictable. And sometimes changing things just makes them better and you sort of thank that, but you get frustrated with it at the same time. You can also use multiple solvers. So one of the nice things about SAW actually is that it has a whole layer that serves as an interface between SAW and a number of different solvers. So any given proof will likely make use of Z3, CVC4, Yikes, ABC, sort of any combination of those that lets us get our proofs through. And then the other one is that it enables better composition, and I'll explain what that means in a minute. And as I mentioned, in these efforts, we didn't want to change the code. There are some users of SAW who use changing the code as almost their sole method of getting proofs to go through, and that's actually a really nice way to use the tool. It just wasn't an option for us in the efforts that we're talking about. So in absence of being able to change the code, basically what we had to do is change our view of the code once our tools had interpreted it. And we do this through rewriting an uninterpreted functions. So this is sort of another view of that equivalence that Mike was showing us earlier, the equivalence between the specification and the low-level implementation. And what usually happens is that there's some bit inside of there that we can show this equivalence on. So maybe there's a function that gets called deep down the call chain, and we can show that that is equivalent to some function of the spec. What we can do, if we've gone ahead and proved this equivalence, so this we prove just as if it was the full program, even though it's only a fraction of what we want to prove. Once we've proved that, we can actually go locate those terms in the two programs that we want to prove, and we can use that equality to replace the subterm by the specification. And this can actually greatly simplify things. And even better, in a lot of cases, we don't actually care that much what's going on in there as long as they're both doing the same thing. So in a lot of cases, what we can do is we can uninterpret these functions. We can more or less hide away the body of what they're doing. And as long as they're being used in the exact same way on both sides of the equation, we'll still be able to prove this equivalence. This really simplifies things for the solver, and it actually is the main way that we get proofs to go through when they weren't going through. So this is one example of how we've done this. This is a function from SHA 384. It's more or less from all the SHAs. And this function is called S0, and all you can see it's just a few rotates, basically, and you XOR those together. SHA is basically a information blender. It just takes all your stuff and mixes it around until you have no way of unmixing it, more or less. And so this is one of the steps that gets composed to do that. And so up on top, we see we have a Cryptol. It states it pretty nicely as some shifts. In the bottom, we have the actual implementation, which is Perl, that is used to generate assembly. The Perl decided that if you rearrange things to do smaller shifts, it was going to run faster. So you can see that this is stated in a slightly different way. But this equivalence is actually really easy to prove. But one thing is saying this is one of many sort of ways that things got optimized depending on their context and the implementation. So when we tried to do the proof for SHA, we sort of had to recover all of these S0s. These S0s all got blown up. They got unfolded in the code. They got interleaved with other instructions. And that was making the proof really hard to go through. So in the case of this S0, we wrote a bunch of rules that allowed us to turn this bigger, complicated thing back into S0 and then hide it away within S0. So this was this process of rewriting and uninterpreting. And for a lot of our proofs, this was one of the main tools that we had to use. The final tool is composition. And composition is a really nice, intuitive way to think about proofs. Basically, the way that you think about it is we build up programs function by function. We should be able to build up proofs function by function in exactly the same way. So this is an example of a program that with a call tree. One function calls another function. And all we do in proof composition is we write a proof for each subfunction, and then we kind of glue those together in order to build an overall proof. And what this looks like in general, you can sort of think of each proof as a number of requirements on what needs to be true in the state when it's called, and a number of guarantees on what's going to hold once the program has been called. So what you do is you write a proof for your inner function, and then at the point where you call that from the outer function, you have to actually do the step where you say, I proved this inner function works if x is greater than 3. Now the caller needs to be able to show that it knows for sure that x is going to be able to be greater than 3. And you sort of bubble this all the way up until you get all the way up to the top level proof that you want. The main way of modifying your program to make it more provable is generally just extracting things out into smaller functions that are easier to prove, and then putting them back together with this composition approach. There is a bit of a cost to composition. It's pretty well described by this example. This example is two different ways to represent HMAC or SHA or even AES. They tend to have an init, an update, and a final function. This is to enable processing data sort of block by block instead of having to take it all at once. But generally in the literature, they're described as these monolithic functions. And the key insight here is if you look at the monolithic function, it takes as input only a key and a message to give you your output. But when you do this iterative version where you're going to sort of build up your hash iteratively, or you're going to build up your MAC iteratively, all of a sudden this state variable. And we really want to view functions from the outside and reason about them from the outside. And so the appearance of this state variable, the state type, actually makes the verification a lot harder for the people doing the work, because all of a sudden they have to start reasoning about this state, when before it was tucked nicely away in the function, the tool might have just dealt with it all on its own. So this is just to sort of wrap up. If you kind of thought this was cool and you're wondering how you can maybe do something like this in your own code or in your own work, this is sort of the last step in what you should be doing. This kind of deep formal verification. It's expensive, and it's the highest level of assurance you can get, and it takes experts to do. So if you need it, you should use it, but you should sort of be sure you need it before you go down this road. And this is kind of a description of what the road to sort of understanding that you need formal verification is like. And this is a sort of set of recommendations that I think you could recommend for almost all software. The very first step is to design your system intentionally. Before you write it, think about what you want to do. Sometimes this can look like prototypes. Sometimes this can look like design documents. I think every company and individual has their own sort of culture around this. And then the next step is think about properties. Think about, like, if I were going to try to prove something about this code, what would I prove? If I were going to tell something, my code has this property, what would I tell them? What one sentence would I say? I can promise you my code does this, or I can promise you my code doesn't do this. Try to write those down as well. The next step is to kind of think about what could go wrong. Think about what the threats are to your system. Think about what the untrusted inputs are. Think about what sort of surprise failures could cause you a big problem. And then sort of based on the properties and based on the threat model that you've viewed for your code, come up with a plan for how you can convince yourself that some of these properties hold and that some of these threats can be excluded. This is kind of a tool set that you can use to sort of go down and think about maybe how you're going to approach some of these things. Usually the very first line of defense, the very first way to make sure you maintain some of these properties and make sure that some of these threats can't be exercised is just through code review and documentation. Feeding your properties and feeding your threat model into code review and documentation is a wonderful tool, and it's going to save you from a lot of headache down the road. The next step, which also does feed back into code review and documentation, basically everything here can kind of feed back up, is just writing good tests. Again, if you have properties, you might be able to turn those into executable specifications and actually test that some of those properties hold. And then you might realize, hey, look, I can actually do this automatically. I can actually feed random inputs, or I can feed random good inputs or random bad inputs into my program, and I can check to see if my properties held when the program ran. So fuzzing or property-based testing is a great way to accomplish this. The next step is to do modeling or model checking. So tools like TLA Plus or P that we've heard of at this conference are great for writing down sort of abstract views of your system and then reasoning about those and ironing out some bugs. This is a particularly useful way to deal with concurrency problems, which are quite hard to deal with in any other way. And then you can look at maybe doing some symbolic testing. So there's tools like CBMC, Galois has Crux. There's some tools that sort of do almost like unit test versions of what we did in these full verifications. And then finally, you can say, like, well, all of these didn't meet my needs for correctness. Now I'm going to go into sort of a full program proof sort of approach, or correct by construction. So I think I will stop now. If anybody has questions, now would be a wonderful time to ask those. Yeah, so you can, the question is kind of how much the formal verification needs to be coupled to the particular implementation. This layered approach lets you, to some extent, reuse things to the extent the implementations reuse them. The bad news is if the implementations are completely different, then your proofs are just going to have to be different. Generally, you do still want to use the same specification. So one of the things that's worth mentioning is Galois has a public Cryptol specifications repository, and anytime Galois does a proof, the goal is to get the proofs to be in that repository, and so multiple proofs of, say, SHA-384 should point at exactly the same specification. Sometimes if they share optimizations, you can sort of draw the arrows a little farther down the tree and save a little bit of work, but at the very least, you want your specifications to be sort of consistent and public and obvious. Yeah, so in this case, AWS contracted Galois to do the work. There are a number of ways. Blockchain has been a great source of funding for this kind of work as well. That BLAST library was one example. There is a lot of work at AWS at the moment in verifying this kind of open infrastructure. In general, when people want to do verification, they tend to also want that to be open. Verification ends up largely being about trust, and there's sort of no point in saying, we did a lot of really great work, and so now you don't have to trust us because we proved our code correct, but you have to trust us that we did this work. It's kind of a nonsensical thing to do. So this work does tend to be open. On the individual, if you're an individual that wants to do this, as Mike mentioned, Galois is hiring, and AWS has a number of positions as well. So definitely reach out to either of us if that was a personal, not an organizational question. Yeah. You want to take the next?
Yeah, that's roughly the right idea. So you have a variable, instead of having variable, input variable x be 7, you have input variable x and you hold it as just x. And then in your output formula, you have some constraints on what x could possibly be. Yeah, that's roughly the idea.
It's not a lot different. The main reason, the main difference I'd say is that because we're reasoning about C, symbolic execution requires a lot of work. So like when you do simplification in Coq or most pure functional languages, it's generally like beta reduction, like I'm just going to plug in my variables, or expression reduction, or something along those lines. With C, you have to have a whole model of what the memory is doing. And you have to have a whole model of all the things that might go wrong when you're accessing memory. And so you have to model all these things, but part of the goal of symbolic execution is to strip all that stuff away and to turn it into something that you can evaluate only with beta reduction and expression reduction. So that's sort of the difference. The goal is actually to get to that point where they're equivalent, and that's where we do our proofs.
I think that's a great question. So we are actually verifying at the LLVM level rather than at the C level. But the trusted code base is still very significant. You have to believe that LLVM is being executed correctly. So I would say, the sort of warning sticker on this is that, when we say that there are no bugs, there's a big sort of asterisk there that says, assuming that the tool is correct, assuming the compiler doesn't mess things up. So what you can get with formal verification in general is a dramatically higher level of confidence, but there are lots of places that are in your trusted code base that can't be eliminated really, until we reach the formal verification utopia when all hardware and software is completely correct. So we make those kind of trade-offs because that's what makes our projects viable, basically. I think we had a couple of examples when we were working on this BLAST library where they weren't bugs exactly, but they were certainly things that were strictly speaking undefined behaviors. So our model tends to be quite strict. So the C compiler is usually more permissive than than our model is. And so, but the other thing is that one of the reasons that Jerry was just saying this kind of progression of correctness, it's much easier to prove your software correct once you're already pretty confident it is correct. Now I think that means that mostly when we get to the software, when we get to OpenSSL derived code, it's been tested for many, many years, and you want to kind of get to a level of correctness, but mostly there aren't that many bugs, or there are ambiguous things, but I don't think we've ever found a real showstopper, and maybe you remember something that we found.
I think farther back there were some pretty specific bugs in some elliptic curve code we verified that were sort of one in a trillion kind of things where maybe a carry wasn't being done right. AES and SHA, there's nowhere for that many bugs to hide, but yeah, once you get into elliptic curve, there's a lot more sort of subtle mathematical mistakes that can occur. Yeah, as Mike said, though, we normally don't go into these expecting to find a lot of bugs. You view this sort of thing as sort of the very last step in confidence, and if you're sort of willing to go to that length, you've probably already gone to a lot of other lengths to iron out bugs. Great. Thanks so much, everybody.